Andrew Clarke, telling us about the G2 matrix on Bryant-Salamon manifolds.
So thanks very much to the organizers, and I guess I'm the final speaker, so I should thank the organizers on behalf of everyone. So Pedram and Henrique Bursztyn and Reimundo, I guess the local guys, and Peter and Mathai, who've brought everyone from Australia. So thank you very much. I'm going to speak about instantons on the manifolds of Bryant-Salamon. On the Bryant-Salamon manifolds. And so specifically, these are G2 instantons, and so the metrics of Bryant-Salamon were the first complete examples of Riemannian metrics with precisely G2 holonomy, with full holonomy G2. And they appeared in the late 80s, and since then, sort of gauge theory in these special geometries and these special settings has become interesting and become more widely studied. But there's still a relative lack of examples of these gauge fields, and so I'll give a description of some explicit constructions for instantons on these manifolds. So to start, I'll say something about the Riemannian holonomy. So the holonomy classification came in the 1950s by Varghese, so modulo a few hypotheses on the manifold of irreducibility and not being locally symmetric, etc. There are 7 possibilities for the Riemannian holonomy group. So SON, UN, SUN, SPN, SP1, SPN, I guess I'm forgetting. And so these all exist on sort of 2n-dimensional manifolds, real 2n-dimensional manifolds and real 4n-dimensional manifolds. But the 2 exceptional cases are G2 manifolds that only exist in dimension 7 and spin 7. The Riemannian manifolds that, at least that only exist in irreducible cases in dimension 8, and so they're the exceptional sort of geometries. And so the question, so I'll just explain a little bit at least about what is the group G2. And so the most concrete, I think, realization of the group G2 is as the automorphism group of the octonions. So the octonions being an 8-dimensional normed division algebra, and so the octonions are obtained from the quaternions in the way that the quaternions are obtained from the complex numbers by the Cayley-Dickson process. But as in that case, you lose the associativity condition, and so the octonions are non-associative, which I guess makes it a little bit more difficult. But and so these are so they're linear maps on R8 that also preserve the multiplicative structure of the octonions. So, but G2, it preserves the identity in the octonions, and so it acts on the orthogonal complement, which is R7. And so this is the fundamental representation that gives the holonomy representation. But then multiplication, so multiplication sends R7, or sends or the cross product that you obtain from the multiplication on R8 sends R7 to R7. So the multiplication on R8 determines a vector cross product on R7, But if you raise an index, then this gives a 3 form. This gives a 3 form on R7, or R7 star, by phi of x, y, and z as the product of x, the inner product of these elements. And so you can write this as dx1, 2, 3 plus dx1 times by dx 4, 5 minus dx 6, 7 plus dx2 times by dx 4, 6 minus dx 7, 5 plus dx3 times by dx 4, 7 minus dx 5, 6. And so this is not especially illuminating writing out the multiplicative, this rule that gives the 3 form. But what I want to emphasize by writing out this form is how the multiplicative structure via the cross product on R7 can be reduced in a certain way to sort of a 3-dimensional component spanned by the first 3 vectors, dx1, 2, and 3, and then in the other 4 directions, this form is related to the anti-self-dual or the self-dual anti-self-dual forms that appear on R4, and so an expression of this form will come up in a second. So another and so G2 is equal to the stabilizer of this 3 form, and so G2 is G2 being the group that preserves multiplication, it preserves the vector cross product on R7, and you can also show that it preserves the metric, and so necessarily it's the stabilizer of this. It's the stabilizer of this 3 form. Another way of realizing the group G2 is that if you have if you consider spin 7 acting on the spin space, the spin representation on R7, which is so I'm not sure of the best notation for this, but you take the fundamental the spin representation of spin 7, and if you take a fixed non-zero vector here, then G2 is also the stabilizer of a fixed spinner on 7 dimensions. And so each of these conditions will be related to the holonomy condition on Riemannian manifolds. And so on a Riemannian manifold, then the holonomy group is contained in G2 if and only if there exists a 3 form that's pointwise isomorphic to this fixed 3 form on R7, in the sense that at any point there's an isomorphism that sends the tangent space of the manifold to R7, so that the pullback is equal to, of that phi is equal to this phi that you have. So this is pointwise isomorphic to phi, and such that the Levi-Civita connection, so it's parallel with respect to the Levi-Civita connection, and you can make the same sort of conclusion. The Levi-Civita on a spin manifold with the spin bundle, the Levi-Civita connection gives a connection on the spin bundle. Then if you have a non-zero spinner that's parallel with respect to the Levi-Civita connection, then that necessarily also reduces the holonomy to the same group G2. And so, in present company of physicists, then the necessity, or the physical necessity to have parallel spinners necessarily relates very closely so the necessity to have parallel spinners relates those physical situations to having a reduced holonomy. In the Calabi-Yau case, the reduced holonomy is to SU3, where you have a 6 manifold with some parallel spinners. But another way of realizing the G2 holonomy condition is that if you suppose if you have a 3 form on the manifold that is sort of isomorphic to phi at any point there's an isomorphism that relates the 3 forms, then you can say that phi determines a Riemannian metric on M. And this is not really evident necessarily, but given a 3 form that by some isomorphism of R7 to R7 is isomorphic to this one, then just by exterior multiplication and contracting vectors in and taking some 9th roots or something, then necessarily a 3 form that's non-degenerate in a certain sense, then it necessarily determines a Riemannian metric. Perhaps analogous is the fact that symplectic form with a compatible almost complex structure determines a Riemannian metric in 2n dimensions. And so on the manifold, if you have a form that's isomorphic to phi, then it determines a Riemannian metric on the manifold. And then if the form is closed and co-closed, and if it's closed and co-closed with respect to the metric and orientation that phi itself determines, then necessarily, with respect to the Riemannian metric that it itself determines, then it's parallel and the holonomy group of G phi is contained in G2. So this fundamental idea, so if I didn't put the phi there, if I didn't explicitly refer to the fact that the metric that I'm talking about defining the co-closedness is again with respect to the form phi that I'm differentiating, then this looks like a linear condition, a linear differential equation. So it looks like the condition that phi is harmonic, but it's a nonlinear differential system by the fact that phi is harmonic with respect to the metric that phi itself determines. So so that's sort of why I guess finding G2 holonomy metrics is not the easiest thing because of the nonlinearity of the differential equation that you're considering. So the examples. So the examples, I guess, of manifolds where the holonomy is contained in G2, seven manifolds with holonomy in G2. The simplest are just Euclidean space and some tori and things like this. But I guess the simplest or the simplest non-trivial example, or the most difficult, or the most difficult understandable example is of a Calabi-Yau crossed with a circle. And so Calabi-Yau with the Ricci-Flat-Kähler metric has holonomy SU3, and SU3 specifically considered as a subgroup of G2, and so the holonomy is SU3 as a subgroup of G2, sort of acting trivially on that one other factor. For the holonomy group equal to G2, the first example was by Bryant in approximately 1985, and so that example was was given by solving a heavily overdetermined system of nonlinear equations using exterior differential systems, and that this first these first solutions were just sort of theoretical solutions defined on small balls in Euclidean space, and so in the sense that the metric exists, but it doesn't really have any geometry, and so it was non-complete. It was incomplete, and it was just defined on a small ball. And then Bryant-Salamon in 1989, they gave the first sort of complete examples in 1989. And so there are smooth manifolds where the metric is complete and where the holonomy is the full group G2. And so there were 3 examples for holonomy G2 and 1 example for holonomy spin 7. And so the first was the one that I'll pay more attention to in a second was on the manifold just S3 times by R4. And so that's topologically easily understood, but sort of geometrically, according to the construction that they gave, this was the spinor bundle on S3. They wanted to, so they realized the metric by considering this as the spinor bundle on S3. And so the tangent bundle and the spinor bundle are trivial in that case. And then the other examples were of self-dual 2 forms. So the space of self-dual, perhaps anti-self-dual, depending on your choice of orientation. The set of self-dual 2 forms on S4 and self-dual 2 forms on CP2. So these are rank 3 vector bundles over 4 manifolds, and so the total space of 7 are of smooth manifolds, 7-dimensional, and the same sort of way showed that they showed that these admit full G2 holonomy metrics. And then some spin 7 examples, and then then there's the BGGG examples of Brandhuber, Gomes, Gubser, and Gukov. And this is in 2001. They constructed more complete metrics, another complete metric on S3 times by R4. The difference being that with respect to sort of geodesic distance in the manifold, the volume growth in this case is maximal. It's R to the 7 volume growth here, but the volume growth in this case is R to the 6th volume growth. So to a certain degree, this second example is more closely analogous to the Taub-Nut metric in 4 dimensions. So approximately something reasonably similar in a certain sense to the Taub-Nut. So someone can explain that to me later. So these are the non-compact examples that are reasonably well known. The compact examples, the first example is by Joyce, and so this is the Kummer, the generalized Kummer construction. And so in this case, you have a finite group acting on the 7 torus, preserving. There's a 7 torus. So this is a finite group acting on the 7 torus, preserving the flat G2 structure in that case. In certain examples, so for certain examples of groups acting here, then if you sufficiently well understand the singular set here and in such a way as to be able to, then you can. So then you can, so if you sufficiently well understand the singular set in the quotient, sufficiently well to be able to resolve the singularities using complex geometry, then without, just with some bump functions, you can construct approximate solutions. You can construct approximate solutions here to this set of differential equations, depending on where this phi depends on a parameter epsilon, which is essentially the size of the exceptional divisor that you obtain when you do the blow up, but then using some PDE, an iterative sequence using PDE, then you get an exact smooth solution to the system, to that system over there. And then the final, then the other example of Kovarev, and so Joyce's construction was in 1995, and then developed further in the exceptional holonomy book from 2000, I guess, and then Kovarev in 2000, together with Corti, Haskins, Nordstrom, and Pacini in 2013. So let's have apostrophes. So these two papers developed the idea of a twisted connected sum constructions, and in this case you have asymptotically cylindrical Calabi-Yau, so Ricci-flat Kähler metrics, 6 dimensions. You cross them with a circle to get 2 different 7 manifolds with SU3 holonomy. If you can just topologically, well, not topologically, but if you can join the asymptotic ends together in a sufficiently well-behaved way, so as to get an approximate G2 metric, sort of analogous to this one, then you can perform Joyce's iterative scheme to obtain a G2 holonomy metric, a full holonomy G2 metric. But after the heavy PDE work of Joyce, to my understanding, the difficulty in this case lies in the identification at infinity, which is to do with hyperkähler rotations or hyperkähler involutions or anti-holomorphic involutions on K3 surfaces, which is sort of what happens at infinity here. Right, so I want to understand gauge theory. So I want to understand gauge theory, and so to a certain degree, this is, so what I'll talk about is by close analogy with self-dual, anti-self-dual instantons in 4 dimensions. So, for n equals 4, I guess we have a principal G bundle. Have a principal G bundle here, and a connection A that is connection. And the equation that I want to solve, the equation that one wants to solve is of self-duality, or anti-self-duality, depending on your choice. And so this equation makes sense because there's the decomposition of 2 forms in 4 dimensions into self-dual and anti-self-dual parts. And so the connection is a bundle value 2 form, and it's an instanton. It's an instanton if it takes values in one of these 2 components. And essentially, we have this decomposition because the adjoint action of SO4 on its Lie algebra is not irreducible. And so that's a special fact for Riemannian geometry in 4 dimensions. And so we have this decomposition that's well defined on any Riemannian 4 manifold. And so the fundamental solution of the BPST instanton is where the connection is given by the imaginary part of x times by dx bar divided by 1 plus x squared. And so really thinking of it this way is probably more in tune with thinking of vector bundles rather than principal bundles, where the connection that you want is exterior derivative plus some one form that takes values in SU2. And then if you differentiate this out, then you can show that you get lots of dx, wedge dx bar with multiplication, sort of quaternion multiplication, and the consequence is that the curvature lies in this factor. Pardon? Yeah, so BPS are Belavin, Polyakov, Schwartz, and Turin. Yeah. And so so I don't know the chronology or the correct attribution, but it's also known as the 't Hooft solutions, but maybe that's a misattribution as well. They're pseudo-particle solutions in 4 dimensions. And so in 7 dimensions, for n equals 7, you don't have a decomposition like this on 2 forms. Well, you don't have a decomposition like this on 2 forms when you consider the two forms, or when you consider lambda 2 as a representation of SO7. SO7 acts on the adjoint representation. Adjoint representation of SO7 is irreducible. But if you consider the representation of G2 acting on wedge 2, on lambda 2, then there is a decomposition, essentially because G2 is a subalgebra of SO7. So, and so if M phi is a manifold with sort of G2 structure, then lambda 2 I can write as in terms of these 2 irreducible components, irreducible under the representation of G2, where the first component here is of those 2 forms that are contractions of vectors into the 3 form. So this first factor is just contractions of vectors into phi, and this factor corresponds to the inclusion of G2 as a subalgebra of SO7. And so in this context, on manifolds with G2 structures, I can consider connections on principal bundles or vector bundles whose curvature satisfies a relationship similar to this one. So a connection, nubler now, is a G2 instanton if any of the following hold. So if the curvature lies in lambda 2, 14, I guess, times by endomorphisms. And so this is here I have a vector bundle here. And so if the curvature at each point takes values in this particular subspace with values, sort of vector values or endomorphism values, or if the curvature satisfies this relationship, this equation, and so this is the most closely analogous condition to the self-duality condition in 4 dimensions. That wedge product with phi and then the Hodge star defines an endomorphism on 2 forms, and a 2 form lies in this subspace if it's an eigenvector with eigenvalue equal to 1. So the other factor is also an eigenspace for value -2, I think. Another condition is that the curvature times by the Hodge dual 4 form in 7 dimensions, that this is equal to 0. So multiplication of 2 forms by the Hodge dual of the 3 form. This is a 4 form, and so multiplication here sends 2 forms to 6 forms. At each point, the 6 forms are 7-dimensional, and it's going to act as an isomorphism on this space and by 0 in this space. And so something lies in this subspace if it's in the kernel of this operator, of this linear map. And this is the linear, and this is the condition that's most appropriate, or that facilitates the G2 instanton condition, also the gauge theory in 7 dimensions. Also relating it to spinors on 7 dimensions. If psi is a parallel spinor or non-vanishing, if psi is a non-vanishing spinor that determines a G2 structure on the manifold, then this condition is also equivalent to the Clifford product of the two form acting on the spinor is equal to 0, where you take Clifford multiplication there. This is another way of realizing it. But ultimately, I want to consider this final equation. So some more history of sort of gauge fields in higher dimension. The first time sort of the instanton conditions were considered in dimensions greater than 4 was in 1983 by Corrigan, Devchand, Fairley, and Neutz. And so this is 1983. So this even predates any sort of understanding, any sort of understanding of G2 holonomy metrics. This even predates Bryant's original construction, just local construction of G2 holonomy metrics. And so they were the first, as far as I know, to just write down an instanton condition, which I think would be related to non-vanishing spinors. But then in 1995, Gunaiden and Nikolai, they gave a G2 analog, or an analogous construction to the fundamental solution in 4 dimensions. They gave a very similar construction in 7 dimensions. So this is of a so this is a G2 instanton on R7 with structure group G, and so the structure group of the principal bundle on which it's defined is actually equal to G2 itself. But this is, and the symmetry group, and so this is spherically symmetric on R7, or spherically symmetric in the sense that it's invariant under the action of G2 on R7. And it extends apparently to, and it extends to a G2 connection on the 7 sphere, even though the 7 sphere doesn't admit a G2 holonomy metric. Right, so for like ADHM type. As far as I know, there's not. I think for one reason, the ADHM construction is via you interpret it as a moment map condition. and so you consider. Well, so I think Henrique knows some things about this. I don't think that there are sort of results at the moment, but I think it's so things like num transform on tori in 7 and 8 dimensions. They're sort of interesting questions that we've discussed at different times, but as far as I know, there are not specifically results. So where was I? So there are these examples of G2 instantons that are not explicitly related to the geometry of the space in which they're defined, but even the Riemannian curvature tensor for a manifold with G2 holonomy that will satisfy these conditions by the curvature being infinitesimal parallel translation. And so, but then there were the papers of Donaldson and Thomas, together with Donaldson and Siegel. And so in the mathematical literature, I think this was the first point in which any sort of reason to study for differential geometric reasons G2 instantons. It was the first time. And this was in the second. So this was 2000. This is 98 and 2009. So these papers were I guess the progenitors of the study of differential geometry in high dimensions, or of gauge theory in high dimensions, but specifically from differential geometric point of view, or with the aim of resolving differential geometric questions. So, and then more recently, I'll write Sa, Earp, and Walpulski. Don't know the exact dates, but it's sort of from 2011 in the two cases. So Henrique has studied the G2 instantons on the asymptotically cylindrical Calabi-Yau's to work out what types of connections on each of the components are necessary for to do the twisted connect sum construction of the manifolds together with a gluon construction for the instantons, and the details there are really quite subtle in terms of the intersection theory of the moduli spaces of the connections at infinity. So it's relatively delicate. Walpulski also studied. So initially in his first things he studied the G2 instanton condition, but on the Joyce manifolds, on the Kummer, the generalized Kummer construction, and then in a subsequent work of Sarup and Walpulski, they constructed some examples on some various manifolds. And then to finish up on this history lesson, Gonçalo Oliveira studied monopoles on the Bryant-Salamon manifolds. And so this is in 2014. And so to go with the G2 instanton condition, it's also possible to define G2 monopoles. And the monopoles that Gonçalo studied were primarily on the 7 manifolds given as rank 3 bundles over the 4 manifolds. So the lambda 2 plus over S4 and CP2. He also studied the instanton conditions on these, but I think showed a rigidity or sort of. So I won't say what he did, but he also studied instantons on these manifolds. But the principal results were on monopoles in that case. So the one remaining. sort of example tying these things together is of the other Bryant-Salamon manifold, which is S3 times by R4. So to understand this geometrically for the construction, it's I'll write this as a total space of the bundle. And so if F tilde is the spin bundle, the spinor bundle, not the bundle of spinners, it's the spin structure of the on S3. And then I can consider with an associated bundle X or M, X, which is so via the associated bundle construction, I can consider a vector bundle also defined over S3, but whose fibers are four-dimensional. And so X is a smooth 7 manifold, but also importantly, X canonically admits a principal bundle with structure group SU2. And so I'll consider this space as a principal bundle over X with structure group SU2. And so I can consider so phi, I guess. Phi is the Levi-Civita connection on F, considers as a one form on F with values in the imaginary quaternions. I can consider phi. I don't really need to consider, but omega I can consider as the soldering one form, which is a one form defined on F that takes values in the imaginary quaternions, and essentially it's invariant or equivariant. It's equivariant by the action of SU2, but essentially it detects it detects horizontal directions in F, but directions in the S3 factor. And then the final equivariant one form that I'll consider is sort of dA minus A times by phi. This is essentially redundant, just that you need just in order to get an equivariant one form that's I guess zero in the correct direction. But alpha is a one form with values in the quaternions, but it detects these other directions. So with these equivariant one forms, I have a co-framing for the manifold, and so it's sufficient data to consider the Riemannian manifold on X, but using forms upstairs. And so these are basically the horizontal directions, so the S3 directions, and this detects the fiber directions. And I can consider three forms by omega 1, wedge omega 2, wedge omega 3. This is an imaginary quaternion valued one form, so these are just the coefficients of I, J, and K, and gamma 2 is omega 1 times by alpha 0, 1 minus alpha 2, 3 plus omega 2 wedged alpha 0, 2 minus alpha 3, 1 plus omega 3 wedged alpha 0, 3 minus alpha, 1, 2. So now omega and alpha are equivariant under the action of SU2 on this principal bundle, but when I consider these three forms, these are these are invariant under the action of SU2, and so they descend to three forms on the base manifold downstairs. And so the theorem of Bryant-Salamon was that for f a function of the radial direction in the radial direction in H, but this is given by 1 plus r to the power 1 over 3 plus and g of r is equal to 2 times by 1 plus r to the power minus a sixth. For these functions, the three form f cubed times by gamma 1 plus f times by g squared times by gamma 2 is a non-degenerate three form on the manifold, non-degenerate in the sense that this is a well-defined three form on the manifold X. At every point, it's isomorphic to the fundamental three form in R7. So this defines a G2 structure, on X, and satisfies d phi is equal to 0 and d star of phi is equal to 0. And so necessarily the metric induced by phi on X has holonomy contained in G2. Furthermore, they show that the holonomy is actually equal to G2 because there are no, with respect to the metric, there are no parallel one forms which would reduce the holonomy further, which would reduce the holonomy to a proper subgroup of G2. And so F tilde is just the spin structure on S3. So topologically, it's just S3 times S3, but considered as the principal bundle. So for instantons, on this manifold, we'll consider. I want to consider an imaginary quaternion valued one form, which is the imaginary part of A times by alpha bar. So on this manifold here, on the product on this manifold here, which I'm considering a principal bundle over X, A is just the projection onto the quaternion factor. So A is a quaternion valued function upstairs, equivariant. And alpha is a quaternion valued one form, essentially the covariant derivative of A considered as a section of the correct bundle. And so, but when I take the conjugate, I multiply them together, and I take the invariant, and I take this imaginary part of the product. This is an imaginary quaternion valued one form on this thing upstairs, but really this is invariant under the action of SU2. So this is an imaginary H valued one form, but that descends to the manifold downstairs. And so I'll consider the connection. So we'll consider connections on a trivial bundle, a trivial vector bundle over the manifold that are of this type, just a regular exterior derivative, but plus this Lie algebra valued one form. So right, this says A, so a Lie algebra valued, an imaginary H valued one form. Then no, so just in section 3 of the paper I used F there, and then in section 4 I used a different F here. So I'll put H. So I'll consider some other function also dependent, or also only dependent on the radial factor, but by just guessing, by guessing a solution like this, I can reduce the PDE that comes from the G2 instanton condition to just an ODE in this unknown function. And so the theorem is that for h of r equal to 2 over 3 times by r plus 1 plus a constant times by r plus 1 to the power 1/3, then this connection, which we'll write, this connection depending on this parameter c is a G2 instanton. And so this is a G2 instanton on a trivial bundle over X, but whose structure, so it's a trivial bundle, but it's a connection whose structure group is SU2. So it's perhaps more geometrically, I don't want to say it's more, it's as geometrically interesting as this other case, because the structure group of the instanton is sort of the smallest sort of compact simple Lie group that you would want to study. And so with structure group SU2. So just before I finish, I'll just list some properties and observations, etc. So the condition to be the G2 instanton is a nonlinear PDE, is a nonlinear PDE, but by this sort of judicious choice of the invariant one form with values in the imaginary quaternions, and just here it's reduced to the ODE that the first derivative of h plus h squared plus 1 over 3 times 1 plus r times by h is equal to 0. So it's a nonlinear EDE, ODE, but possibly the nonlinear ODE that's the most sympathetic ODE that you could hope to come across. And so this is a Riccati type, and so there are sort of really easily there are classical ways of integrating it, and so you get that solution. But the observation is that that this solution depends on this parameter c, and this is a little bit strange because using index theory and calculating moduli space, the moduli spaces of G2 instantons on compact manifolds, generically G2 instantons would be isolated, that the moduli space would generically be zero-dimensional. But these appear in a family, which is a little bit strange. I'll mention that in terms of some further work of Gonçalo and Jason Lutte. But
sorry, are they gauge and equivalent? It's the moduli space modulo gauge, right? That should be discrete. It's not at all surprising that they come in the family as connections.
As connections, yeah.
Connections modulo gauge would be surprising.
Yeah, I think the curvature densities are different.
Yeah, they are not gauging.
They're not.
They are not, but it's an orthodox space. It's an
Yeah. Yeah. I think you can see that they're gauging equivalent by the fact of the densities of the curvatures being different. But then the Bryant-Salamon manifold, the BS manifold, is asymptotically conical with the asymptotic to the nearly Kähler, or asymptotic to or a cone over the nearly Kähler S3 times by S3. So it's asymptotic to a cone over this manifold. And so this is not just the product metric, the product of two round spheres, because the product of two round spheres has isometry group SU2 4 times. But you can have, on the product metric here, you can have SU2 acting on the left and the right of both of the factors. But the isometry group of this is lower, it's SU2 3 times. And so this has a nearly a non-integrable or a torsion SU3 structure on the product here, and for any of the connections, or any of the connections, or all of the connections are asymptotic to Hermitian-Yang-Mills connections, or to the same Hermitian-Yang-Mills connection on S3 times by S3, and so that's the canonical connection, using certain language of invariant connections on homogeneous bundles. It's referred to as the canonical connection. And so we have a family of connections so that at infinity they converge, and they converge to the same asymptotic limit. The connections, and so these connections are highly symmetric. With SU2 cubed symmetries, and a theorem of Jason Lotte and Gonzalo Oliveira says that among from a paper that came out this year, say that these connections, that if you consider SU2 cubed G2 instantons on S3 times by R4, then you either have an element of this family or another family, depending on how they cross the zero section. So these are all symmetric connections. And this is sort of paying attention to how they extend across the zero section, which is A equal to 0 in this or R equals 0 in this case. The metric is of the G2 metric. Yeah. It's the same SU2 cubed. So further results of Jason and Gonzalo are that there's a there are bubbling phenomena. As the parameter c goes to infinity. And so these are bubbling phenomena in the sense of sort of analogous or in the same flavor of the sort of removable singularity type theorems of Tau and Tian. But those results are not directly applicable in this case, but at least in this case everything is explicit. And so the bubbling phenomena is that as you, along the, so one of the results at least, is that along the four-dimensional fibers, if you scale the R4 at the same time as taking a sequence of these connections with respect to this parameter, then the sequence will converge together with its derivatives to a standard four-dimensional instant, to the standard BPST instanton. Right, and so I think that's a pretty nice result, just relating these examples to the standard four-dimensional gauge theory along the fibers. So I'll leave it there.